Okay, so sorry for the slightly late start. So today I was going to finish up chapter 6 entirely. So I made a post yesterday containing the three problem sets that I had mentioned before. The idea is next Thursday, I think, I'll have some extra time during the live lecture where you can ask me questions from any of the problem sets um, that you wanted to talk about. Those problem sets are meant to give you a good range of problems on the remaining material. So the plan for the semester is to finish through chapter 8. You'll notice that in the problem sets, the chapter 8 problems that I assigned, I only assigned like a couple of them, or I only assigned like 1 to 2 problems from each of those sections. You'll see why that is. Chapter 8 goes really quickly because it's a lot of quick. So the way that chapter 8 is divided, the sections are very, very small. Like a good like 4 or 5 of those sections are only a page, page and a half at most. So the sections are very small because, for instance, an entire section will be like the Taylor series expansion for the logarithm, for instance. On account of that, chapter 8 goes really quickly. It's not that I'm trying to like pile a bunch of work on you. It's just that's how chapter 8 is split up. So plan is to finish through chapter 8, which means that the chapter 9 material I had originally planned to cover will be sort of I don't think that I will quite get to that in these lectures. So what I may do is upload some supplemental lectures for the chapter 9 stuff so that you will have seen that stuff, because if you take 411, it will basically begin like right after the chapter 9 stuff. So it's important that you've seen that bit. So I will make up that material that is being nixed from like full coverage. And what I'll do, like I said, instead is I will upload some supplemental material to help you with that in the event that you're going on to 411 and want to see that and don't want to be shortchanged. So anyway, finishing FTC I and II. So you already know what is meant by fundamental theorems of calculus. So you might remember that there's 2 of them. One of them has to do with taking the integral of a derivative, and the other has to do with taking the derivative of an integral, right? So both of them, both of them are saying something nice. Taken together, they're saying that integration is the inverse operation to differentiation, right? So this is something that you've known for a long time in your math career. And you might even remember the exact statements of these things, but now we're going to prove them. Okay, and so to stress, the way that we've treated this material in this class so far is right now basically our main tool for even attempting to evaluate an integral is the Archimedes-Riemann theorem. But the problem with the Archimedes-Riemann theorem is that in order to actually compute with it, we are computing the integral as a limit, right? So Archimedes-Riemann has us computing the integral from a to b of f as a limit of either the upper or lower Darboux-sums. I'm just going to use the upper. Right, so Archimedes-Riemann theorem says that if f is integrable, then, so it's actually an if and only if statement, but if f is integrable, then there exists this Archimedean partition, or this Archimedean sequence of partitions P sub n, and in that case, then the integral from a to b of f is the limit as n goes to infinity of the upper Darboux-sums, for instance, of f associated to this Archimedean sequence of partitions. But the problem with using this to actually evaluate integrals is that computing these upper and lower Darboux sums is really, really hard. In fact, except for the very special cases we talked about, like the step function or a constant function, or functions with very, very rigid properties, it's hard to compute these things. So yeah, it's typically very hard to compute these upper and lower Darboux sums. So we got to have something better. We got to have a better way of computing. You already know where this is headed, but this is the reasoning for the way that the subject's been treated by us so far. So to that end, so I need a better way of computing this integral. All right. So first, a lemma. So following lemma says that suppose that f defined on the closed interval a to b is integrable, and that the number a has the property that for every partition of AB, we have the following estimate, which is that the lower Darboux sum of f associated to P is less than or equal to A, and that is less than or equal to the upper Darboux sum of f associated to P. Okay. So suppose that you have an integrable function and there's some number that is always bounded between the lower and upper Darboux sums for any partition, so that's important. If this holds for every partition, not just for some. So if this holds for every partition, then what's true? Then it turns out that number a is the value of this integral. Okay. Intuitively, you might get a feel for why this is. In fact, you're probably already thinking right now, well, since I'm thinking about these things, and I know that these things are defined in terms of infs and soups, you are probably, and since f is integrable, you're probably already going through in your head the proof. So let's go ahead and do this. So proof. Okay. By assumption, any a that satisfies such an estimate is already an upper bound for the collection of lower Darboux sums. So a is an upper bound for the collection of lower Darboux sums. Okay. Thus, by definition of supremum, the lower integral is bounded above by a. But a is a lower bound for the collection of upper Darboux sums. Thus, this upper integral has what relationship to A? Well, it bounds A above, by definition of infimum. And now you see what we're going to say here. But F integrable means that, by definition, this is the definition of integrability, right? So F integrable means that these upper and lower integrals are actually equal. But how could that happen? Well, what that means then is exactly this estimate. But both of these end things are actually equal to the integral from A to B of F. Oh, this should be an equal. So the integral from A to B of F is equal to A. All right. So this was really just two definitions slapped together, right? Once you have A satisfying that hypothesis. And it turns out that it's only going to take a little bit of maneuvering to essentially get the first fundamental theorem straight out of this lemma. Okay, so let's do FTC I. So theorem, this is FTC I. I can never remember which one is which, so it is better to write out what it is that FTC I says, and this is the thing that tells you how to integrate derivatives. So this is integrating derivatives. Okay. So let the function big F from the closed interval a, b to r be continuous on its domain and be differentiable on the interior of its domain, the open interval a to b. Moreover, suppose that its derivative, big F prime, is both continuous and bounded. Is both continuous and bounded. Okay. Then the actual statement of the theorem. The integral from a to b of switching to Leibniz notation, big F prime of x dx is equal to big F of b minus big F of a. Okay, so that's the full statement of this fact. Now, really quickly, there's a statement that I technically need here before I can go on. So this is my fundamental theorem 1. Before I continue, A quick aside. There is a slightly more general version of our theorem from last time. Recall our theorem from last time was this proof that continuous implied integrable, right? So the theorem said that continuous meant integrable. Okay, so there's a slightly more general version of this statement that is convenient for us to state now. Okay. So this occurs back in the previous section. This is on page 157. So this is the following. So this theorem says that suppose f defined on AB is bounded and continuous on the open interval A to B, then f is integrable on the closed interval A to B, and the value of its integral does not depend on the value of f at the endpoints. Okay. All right, so this is a slightly more general fact than we showed last time. If you want to see the proof of this, it begins on page 157. So I'm not going to go over that. It takes a little bit. It takes a little bit more work than we did last time for our version of it, but it's kind of similar in spirit. It just has a lot more bookkeeping. Well, not a lot more. It's not that much longer, but has a little bit more bookkeeping. Okay, so this is convenient for our purposes. You'll see why. In fact, one of the homeworks from this section has you thinking about these issues, right? Specifically, whether or not it is needed to assume that this thing is continuous either on the closed interval from A to B, or whether it's okay to say that it's just continuous here. I believe that's one of the things that I assigned. If I didn't, then at least I meant to assign that problem. Okay, so proof of first fundamental theorem. Okay, so what do I do here? Well, big F prime is continuous and bounded. Okay, on the open interval A to B. Okay. Thus, what does that mean? Well, by this more general theorem, so by this slightly more general theorem from previously, from the last page specifically. And so this, to remind you, this theorem. Okay, so by that theorem, it is integrable on the closed interval A to B, in the sense that any extension of big F prime to the closed interval a to b is integrable, and the value of the resulting integral doesn't depend on big F prime. Or rather, it doesn't depend on the values of big F prime at the endpoints. It certainly depends on big F prime. So any extension of big F prime, an extension here just means that a definition that you make that extends big F prime. So that means it restricts to big F prime on the open interval a to b, and then at the endpoints you've just defined whatever, right? So you've just defined big F prime to be whatever at the endpoints. And the reason why you can do that is that any extension you make like that is integrable, and the value doesn't actually depend on the value of f prime at those endpoints. So, and the value of its integral does not depend on the value of big F prime at the endpoints. Or I should say here, when I say this, I mean the extension of big F prime to the closed interval a to b. Because you might say, well, big F prime is not necessarily even defined on the endpoints, and that's true. So what I mean here is that the extension of this big F prime that we're talking about. I know it's slightly confusing, but you can think about why that is. So by the previous lemma, that is the one saying that if you could find a number that was always between the upper and lower Darboux-sums of f for any partition, then that number was the integral. So that's going to be the approach that we take. So by the previous lemma, in order to show the formula in FTC I, it is sufficient to verify that for any partition P of the closed interval a to b, the lower Darboux sum associated to big F prime for that partition P is bounded above by big F of b minus big F of a, which is a lower bound for the upper Darboux sum of big F prime. Okay, associated to P. Okay. So that's exactly what we're going to do. We're going to show this estimate. So let P be a partition of AB using the typical notation. So let this be any partition of the closed interval a to b, and fix an index I. Okay. By assumption, the function big F, which goes from, or I should say is defined on this partition interval x sub I minus 1 to x sub I into R. This thing is continuous. Well, it's continuous on the interval a to b itself. That's one of the assumptions. So this thing is continuous on this interval, or rather the restriction to this interval it's continuous on because it's continuous on a to b. So this is continuous on this closed interval. Okay. and differentiable on the open interval, where I've excluded the endpoints. Okay. Thus, by the mean value theorem, remember, when you know a function is integrable and you want to show some property of that function, or sorry, said the opposite thing of what I meant to say. When you know that a function is differentiable and you want to show some property of that function, some general property that is, your first stop basically should be the mean value theorem. This is kind of the first thing that you should be looking at or attempting to use the second that you have a function that is differentiable. Okay, so mean value theorem is your first stop there. So by the mean value theorem, there is a point c sub I in this open interval, x sub I minus 1 to x sub I, okay, such that big F of x sub I minus big F x sub I minus 1 is equal to big F prime of c sub I times the length of this subinterval. Right? So this pops out of the mean value theorem for our big F. This is going to be the thing that does it. So now it's a matter of bookkeeping. Okay, I know I say that a lot, but when I say that it's a matter of bookkeeping, it means you have some estimate and you're not going to do any more computations. What you're going to do is take the estimate you have and use the definitions that you've built up to unravel what this means, and ultimately this is the thing that leads directly to the statement that we want. So from this point, all I have to do now is just unravel all of the definitions that I've built up to this point, and all the definitions and theorems and stuff that I've built up to this point, and I'm done. So this is the thing that's going to do it. Now by definition of little m sub I and big M sub I, remember these are the defining quantities of the lower and upper Darboux sums. So little m sub I is defined to be what? This is the infimum of the collection of big F prime of x values for x in this partition interval. Now you might say, wait, why is it big F prime here? Because I'm thinking of upper and lower Darboux sums for big F prime, right? And so the little m sub I in question is the infimum for big F prime functional values. Okay, so whatever this infimum is, okay, what do I get here? Well, I certainly know that this infimum is, of course, less than or equal to big F prime of c sub I. Why is that? Recall, c sub I is just a generic point. Now, I say that, and I know that it's special in the sense that I found it using the mean value theorem to have this property that I want, but it's just some point here, right? And what I mean is generic is it's just some point in this partition interval, meaning that if I'm taking the infimum over all big F prime functional values here, this c sub I is just some point here. So it is certainly, this big F prime value at c sub I is bigger than or equal to this infimum, right? This is the infimum taken over all values here, right? And c sub I is just some value in that partition interval. So you see where this is going. So this is less than or equal to the sup of that same collection, but this supremum is exactly big M sub I. Okay. So my supremum of that collection is exactly big M sub I. Okay. Okay. Thus, multiplying multiplying both sides by the length of this partition interval and using our previous estimate. When I say previous estimate, I mean this boxed thing from the past page. Oh, there it is. This thing. Okay. So I shouldn't really say estimate there. I should say identity. So using this previous thing that I've boxed here together with this inequality, what do I get? I get little m sub I times the length of partition, the ith partition interval, is less than or equal to big F of x sub I minus big F of x sub I minus 1. And this is less than or equal to big M sub I times that same length. So I have this inequality for all I. Okay. Using this in times, I can sum each of these as terms in a finite sum to get the following. So I can sum from I equals 1 to n little m sub I times this length of the ith partition interval less than or equal to the sum from I equals 1 to n of big F of x sub I minus big F of x sub I minus 1. Is less than or equal to the sum from I equals 1 to n of big M sub I times x sub I minus 1. Okay. What do you notice? What does this become? So this is going to do it. This is going to do it because what is this? This sum is just the lower Darboux sum associated to big F prime of P. And this is the upper Darboux sum of big F prime of P. And I believe, I could be mistaken here, but there is an exercise, well, maybe it's not here, maybe I am mistaken. There was an exercise that no, it must be from a previous section, but it doesn't require too much thinking. What happens here? So in this sum, these terms telescope, right? And so all I get here is f of my last term, x sub n, which is b, minus f of a. Now that's what I want, but why does it work out that way? So what is this in parentheses? This is big F of x sub n minus big F of... did I label this? How did I label my... I think I may have... Did I label my partition starting at x naught? Let me look back here. I did. I labeled it starting at x naught. Let's not do that. Let's start it at x sub 1. Okay, so here. So x sub... Oh, but if I'm going to use I minus 1, then it has to work out like this, doesn't it? Oh, no, that's fine. Wait a minute. Because of the x sub I minus 1. No, I'm good. So this is f of x naught. There we go. Okay, so crisis was averted. There's no reason to change anything. Okay. So this is f of big F of x of n minus big F of x naught, but x of n is b and x naught is a. So this is it. So we have found a number that is big F of b minus big F of a that is bounded between the lower and upper Darboux sums of big F prime for all partitions p. So what this means is that the integral from a to b of big F prime is f of b minus f of a. That's it. All right, that was the thing we wanted to show. So that's FTC I done. All right, that's good. So I'm not going to go over the applications of this in detail. You can have a look at the couple of examples. You have spent a decent chunk of your life using this theorem, so I'm not going to pretend like you've never used this before. So there's a couple of examples. For instance, there's a couple of examples on page. This is page 163. So page 163, there are examples. Again, I'm not going to pretend like you haven't seen this before, but of course I will note that there is an unfortunate fact about this. So while this is really awesome because it associates computing an integral with finding an antiderivative, right? So if big F prime is the function I want to integrate, then big F is called an antiderivative, right? So our F showing up in FTC I is called an antiderivative of big F prime. Okay, so in the context that we've written it here, so what does this mean? i.e., big F is an antiderivative of little f on some set a to b if big F prime of x is equal to little f of x for all x in a to b. So this is the definition of antiderivative. Okay, using this terminology, if big F is an antiderivative of little f on a to b, then the integral from a to b of little f of x dx is big F of b minus big F of a. And this might be the form, or the final form, that you actually remember seeing FTC I in, right? It's stated like this. Now, there is a hang up here, right? So one big issue, or I should say one nice thing, we have reduced computing an integral to finding an antiderivative. So if I want to compute the integral of a function little f, I need to find an antiderivative for little f. Okay. Now you might view this as a ridiculous statement, since to you maybe you even think of the integral as being the antiderivative. But remember, that's not really how we define the integral. We defined the integral in terms of area, and we went through this whole approach using lower and upper Darboux sums. Archimedes-Riemann says that once we had defined what the integral was, right, it was basically if a function f was integrable, then its upper and lower integrals were equal, and what they were equal to was the integral itself. Archimedes-Riemann said that the limit of the upper and lower Darboux sums for an Archimedean partition that was, or an Archimedean sequence of partitions that was guaranteed for a function that was integrable, was how you computed, this integral. Now we're having that we can actually compute it just by evaluating points in this antiderivative. Okay, so as I said, what is the nice thing here? Well, we have reduced that question entirely to finding an antiderivative. So all of that theoretical stuff that was in the background, now we can actually compute this numerically, right, by finding an antiderivative. The problem, so one bad thing, finding an antiderivative means solving a differential equation. Right. Now, talk about differential equations is glossed over by us in this course. You'll note that in the textbook there are chapters that have a star next to them. So we skipped chapter 5 and we're going to skip chapter 7. Those talk about some of the topics in question. So, for instance, differential equations are first discussed in chapter 5. Chapter 7 is basically a treatment of differential equations involving integrals now that they've been introduced. The idea here is that finding an antiderivative involves solving differential equations, and even though we haven't really talked about differential equations in this course, you already know from experience that differential equations, I mean, they can have solutions or not, right? And some of the differential equations, even if theoretically they're not too bad, they may not have closed form, analytic, explicit solutions. Okay, so you're not guaranteed a solution to a differential equation, right? In fact, take the example of the following. Let's take the integral from 0 to 1 of 1 over 1 plus x to the 4th dx. Okay, so there. Here's an integral. What is this? I don't know. Why don't I know? Well, I would have to solve the differential equation. Big F prime of x is 1 over 1 plus x to the 4th. Right? I would need to find big F that satisfies this, but I can't do that. I have no idea what that big F is. Right? So this is a pretty innocuous looking integral, but I can't just do it in a straightforward way here because I have no way of coming up with a big F here, right? And this meshes with your experience with integrals up to this point, right? So if you've ever had me for a class before 410 or 310, then you'll know that I say this a lot. But if you think of trying to do a closed form integration, right? The integral from a to b of function and you get a real number out of it. If you're thinking of trying to do something like that, then if you think of like all the collection of functions that are integrable in a hat and you pull them out of a hat and you ask the question, okay, I've pulled this thing out of a hat, okay, and the question is, can I come up with like a closed form expression for its integral? The answer is no, right? Typically, no. Typically, just a completely typical function that you can integrate, even a completely typical continuous function, right? So the point here is that this is a 1 over 1 plus x to the 4th is continuous. That's why this example is particularly bad. It's continuous from 0 to 1, so it should be integrable, but I don't know how to do this, right, using antiderivatives. So the chance that you're going to pull a function out of the hat that has an antiderivative you could actually compute is 0. And so then you might say, well, how was I able to do all those integrals for all those years? And the answer is selection bias, right? You were asked to do integrals that were specifically nice. And, the focus wasn't put on all of the very, very many integrals that wouldn't work at all. And so that's the one thing to remember in all this, that even though this is very, very nice, we're not totally we're not totally happy here. There are a ton of limitations of the integral, and you know in all of your computations with integrals how sensitive they are compared to derivatives, right? So just thinking at the absolute lowest level when you're computing a derivative of a function, if you screw up a little bit at one step, maybe you screw up an exponent at a particular step, then the final answer you get in your computation of a derivative of a function won't be that off. You won't be that wrong, right? If you did everything else properly, you won't be that wrong. You'll be off in like one or two places, and you'll still be able to proceed. But think about what happens in an integration problem, right? You can think of doing something like integration by parts or any of those old school integration problems that you ever had to do. Doing any of the integration problems, if you made a single algebra error, even changing like a single exponent, there was a good chance you wouldn't actually be able to complete the integration, right? There's a really good chance of that happening. And that's because the integral was insanely sensitive, right? If you changed even a single exponent, you now had an integral that you couldn't do. Right? Okay, so let's continue. I will mostly finish today. There could be some stuff that I have to tidy up next time, but we will certainly start on chapter 8 next time because there's not going to be a whole lot to finish here. Okay, so let us move on. So lastly, FTC II. So this is differentiating integrals. I'm not going to state it quite yet. I have to do some preliminary stuff. So what is the idea of dealing with this, or I should say, what is the idea and how to handle a question of differentiating an integral? What do I even mean by that? So what I mean by that is in defining a function using an integral, meaning that the argument that the function takes in is going to actually involve an integral in some way. So you already, like I said, know where this is headed. But kind of the first thing that I need in order to start talking about this stuff is a mean value theorem for integrals. Okay, so I need a mean value theorem for integrals. So how does this work? So theorem, this is mean value theorem for integrals. This is actually a really nice fact. So what's the mean value theorem for integrals? Suppose that we have a continuous function So suppose this f is continuous, then there is a point x naught in AB such that 1 over b minus a times the integral from a to b of f is f of x naught. Okay. Now, you might remember what the intuition behind this was. So there's a very nice picture on page 166. So picture on page 166 shows intuitively what it is that is going on. So this idea is that you have shaded some amount of area underneath the curve by that point in an equal way. Okay, which is where the mean value comes in, right? You're viewing this as an average of this integral. So if you view this integral as computing area under curve, dividing by b minus a is dividing by the length, right? So this is saying something like the average area, happens here at x naught, right? So to see the picture of this, to understand what's going on, like I said, you can look on page 166. So what's the proof of this? So since f is continuous, we use the extreme value theorem. Which means it has both a max and a min on A to B, right? To choose points x sub little m and x sub big M. These are both points belonging to the closed interval A to B, at which f attains min and max values respectively. Okay, thus, for instance, f of x sub little m is less than or equal to f of x. It's less than or equal to f of x sub big M for all x in AB. Okay. But then by monotonicity of integrals, what does this mean? So by monotonicity of integrals, I can then integrate. So integrating this is just a constant. This is just a constant. This doesn't depend on x. And so integrating this, I get my constant times b minus a. So I get f of x sub little m times b minus a is less than or equal to the actual integral from a to b of f of x dx here. Less than or equal to the same thing here. This is just a constant, so this is f of x sub big M times b minus a. Okay. Taking this inequality and dividing by b minus a, what do I get here? Ooh, I was off screen, so there we go. This is what I have here. So taking this inequality and dividing through by b minus a, what do I get? So dividing by b minus a, that inequality becomes f of x sub little m is less than or equal to 1 over b minus a times the integral from a to b of f of x dx is less than or equal to f of x sub big M, right? Well, what does this mean? Well, let's think for a second. So I have this quantity bounded in this way. So then, what's the meaning of this? How do I get what I want out of this? Recall, the mean value theorem for integrals, the thing I'm trying to show, claims that there is a point, x naught, at which the value of f is equal to this thing. But wait, I'm saying that this thing, okay, that I'm wanting to be equal to some f of x naught for some x naught, is bounded between, this thing takes on, say, range of value. I don't know what the value of this thing is, but it's bounded between these two things, right? So this is just some value, right, that falls in the range of values of f. F is continuous on the closed interval a to b. So by the intermediate value theorem, right, so by the IVT, there exists x naught in AB such that f of x naught is equal to 1 over b minus a times the integral from a to b of f of x dx. So actually, this is something, if we knew what integrals were, we could have proved this back once we had the intermediate value theorem. Okay, so once we had intermediate value theorem and extreme value theorem, we could have shown this fact. Okay, we just had to know how integrals were. Okay, so that's the first thing. Next fact. Okay, suppose that I have a function f from a to b to r, and it is integrable. Define big F of x to be the integral from a to x of f for all x in a to b. Okay. Then f as a function from a to b into the reals is continuous. Okay. It's required that f be integrable for this to work out. Okay. The proof, I'm going to leave the proof of this to you all. You can have a look at this. This is pages 167 and 168. All right. But this is the key quantity that I'm going to define, because when I say that the fundamental theorem of calculus version 2 is differentiating integrals, this is the integral that I'm differentiating. Okay, so I've defined this big F function as this integral from a to x. So the argument it takes in goes here. You've seen this before. Okay. All right, and there's many examples you can come up with explicitly that talks about this. So here is the other fundamental theorem of calculus that is extremely important. Let me box this fact here, because this is kind of the fundamental definition, right, that shows up here. So, lastly, theorem. And this is FTC II. Okay, so what is this? So suppose that the function f from a to b to r is continuous. Then the derivative of the integral from a to x of f. What is this derivative? This is actually just f of x for all x in the open interval a to b. Okay. Okay, so proof of this fact. Using that definition in my previous fact that I left unproved, define big F to be the integral from a to x of f. Okay, so you can do that for all x in the closed interval a to b. So this is properly defined. This is continuous by that previous fact. So let x naught be a point in the interior. Okay. What is the idea? We want to show, well, I want to show this, but using the definition of derivative, what is it, and using this fact that I've rolled up this thing being defined as big F of x, I want to show that the limit as x approaches x naught of big F of x minus big F of x naught over x minus x naught, this is the definition of the derivative of big F, is equal to f of x naught. Okay. Well, let x be a point in the interior that is not x naught. Okay. Then by additivity of integrals, I mean additivity in the sense of, I don't mean linearity, that it splits up across sums. I mean additivity in the sense that I can break an integral apart by intervals, right? So I can split this thing on subintervals. So by additivity of integrals, I get that big F of x minus big F of x naught is equal to the integral from x naught to x of little f. And that's true if x is bigger than x naught. And the negation of this is true if we have the other inequality. Okay. So I haven't talked about the typical things that you're used to here, and I don't actually need to. What do I mean when I say typical things you're used to? I mean typically when you see an expression like this, you would just absorb this minus sign and flip the integration. The fact that we can do that is actually, the fact that we could do that is actually part of a definition that I'm going to make here in a second. So this is what I have just by splitting that integral along the subintervals. So the splits slightly differently, right? There's a sign difference depending on the relative sizes of x and x naught. Okay, we're almost done, believe it or not. So thus, by mean value theorem for integrals, so by the mean value theorem for integrals, what does this mean? There exists a point. We will say this point might depend on x here. So there exists a point C of x between x and x naught, okay, such that big F of x minus big F of x naught over x minus x naught is equal to f of c of x. Okay, but f is continuous at x naught. I mean, it's continuous on the interval itself. So it's continuous at x naught. So the limit as x approaches x naught of f of c of x is actually f of x naught. Thus, I should say, the derivative d dx from a to x of little f at x naught, I should say, this is big F prime of x naught, which is the limit as x approaches x naught of big F of x minus big F of x naught over x minus x naught. But this is the limit as x approaches x naught of f of c of x but that's equal to little f of x naught. So the derivative with respect to x evaluated at x naught is little f of x naught, which is exactly what I wanted to show. Okay. Now, as was mentioned, so as mentioned in chapter 6, and he italicizes this in the textbook, so I thought it was important to have a look at. The principal importance of the second fundamental theorem is that it provides the crucial first step on the road to studying very general differential equations. Okay. So this is a nice fact, and taken together, these two fundamental theorems truly are fundamental theorems of calculus analysis. They are the fundamental things, right? They are the things that enshrine the relationship between the derivative and integral, okay, which obviously you know is very important. Without these, is very hard to practically do much. Okay, so here is a quick definition. You already know these things, but actually the way that we do this for integrable functions is we actually just define the integral from d to c of f is minus the integral from c to d of f, and the integral from c to c of f is equal to 0. We make these definitions. They are defined for us because they make our interpretation of area make sense. And so they lead to all these facts that we want to be true about the integral being true. I don't have to be careful with the relative sizes of the limits of integration. I can just freely flip them using this fact. So this really just makes the notation convenient. You're not doing anything. You're not losing out on anything by just making these as definitions rather than trying to derive them or something. Okay, so these are our definitions. Okay, and that is it. That basically finishes chapter 6. So there's, like I said, there's a couple things here I could tidy up on, and I may do that next time. Probably won't take more than 5 to 10 minutes, and then we'll start chapter 8. So note that means that chapter 7 is being skipped. The chapters that have asterisks in the title are skippable chapters. They are optional chapters meant as supplement. So anyway, so we'll continue on. We'll finish chapter 8 by we won't be totally done with chapter 8 by the end of next week. So it will probably require 3 lectures to be done, but that's the plan. We're gonna steamroll through chapter 8. So anyway, have a look at those problem sets. If you have questions, like I said, you can ask me during one of our live sessions next week. I think I'm gonna do it on Thursday to give you more time. So Thursday's live session next week, I will be taking any questions you have from the problem sets. So have a look at those and let me know. Anyway, so that's it. I think we're gonna stop here. So I will see you all on Tuesday.